Hi everybody, welcome to video number 41. In the last few videos we've been working on a digital elevation model of Mount Shasta, and our ultimate goal has been to compute the volume of Mount Shasta. This might be useful, for example, if you're a volcanologist and you want to know exactly how much magma has been extracted from a magma chamber and erupted in lava flows that actually make up Mount Shasta. So to make a simple volume estimate, we could have used the profiles that we extracted in video number 40. If we just assumed it was shaped like a cone, plug in the formula for a cone, we could make a rough estimate of volume. But ArcMap allows us to make much more precise volume estimates, and that's going to be the focus of this video. So first I'll talk about the theory of computing volume, and then I'll show you two ways to do it in ArcMap. One using zonal statistics, and the other using a direct integration approach in raster calculator. So a little bit about the theory. Assume that we want to compute the volume of part of Mount Shasta here. The first thing to do is to find a reference plane. In this case, that'll be a single elevation, and we want to compute the volume of Shasta either above or below this arbitrary reference plane. So in this case, we'll look to compute the volume of the volcano above our reference elevation, which will be 1900 meters. And the way to compute the volume is to first compute the volume of each pixel in the image above that reference plane. So what's the volume within this pixel between the surface and the reference plane? And to do that, of course, we know that the area of the pixel is just given by its width squared, or delta x times delta y. And this change in elevation, or this vertical distance, we'll call delta z, and that's going to be given by the surface elevation of the pixel minus the elevation of the reference plane. So we can think of that as the height of the pixel above the reference plane. So of course the volume of any one pixel then equals delta x by delta y by delta z. And if we want to get the volume of the whole area, we're going to just sum up the volume of all the individual pixels. So literally we're doing an integration. We're summing up the volume of all the pixels, and that's what this sigma symbol tells us. So let's look a little bit about the workflow to do this, because there's actually a number of steps we'll have to go through. So the first thing we'll do is define that reference surface, and we'll assume it's a flat plane. By the way, in more complicated versions of this, you could assume that the reference surface is any shape that you want. It doesn't have to be flat. You just have to generate a raster of that shape. But in our case, we'll assume it's a plane, single elevation. Then we're going to define an area over which to perform the calculation. We're going to do that either by tracing a new polygon, or in this case, I'll show you an example of how to extract a contour to do that. Then the third step will be to actually estimate the volume. And we'll do that in two ways. In the first example, I'll show you how to do it by just extracting the area and mean elevation using zonal statistics. In the second example, I'll show you how to directly integrate the volume using raster calculator. Okay, so here we go. Here's our DEM of Mount Shasta, and we've got our contour intervals here. As I showed in the example, I'm going to use 1900 meters as our reference plane. That's this contour line here, and I can show that to myself using the information tool. Notice the contour value is 1900. So that was our first step of defining the reference plane. Our second step is to define the area encompassed above this reference plane. And there's two tricks to do this. One easy trick that always works is simply to change the color scheme on the DEM such that you put the elevations above the reference plane one color and below a different color. To do that, I'll go to Properties, and instead of using a stretched color scheme, I'll use a classified color scheme, and I'll make it only two classes, and I'll set the classification break at 1900, the elevation of my reference plane. And then I'll shade everything below 1900 as clear, everything above 1900 as black, and hit OK. Now this gives us a nice two-toned image in which I can see the exact area above my reference plane. All I would need to do now is make a new polygon shapefile and then just do a manual tracing of this dark gray area, and I would be able to get the polygon encompassing the area above 1900. But in our example, we're going to do something a little bit savvier. We're going to recognize that we already have a contour that delineates the exact trace above 1900. So if you look at that gray, it's following the exact 1900 contour. So what I'm going to do instead is actually just export the line of the 1900 contour. Okay, to do this, I'm going to right-click on the contour file, and I made a note of which line it was. It was line number 792. That's it. It's got a 1900 elevation, and I'm going to highlight that so it's selected. Then I'm going to right-click again on the shapefile, go to Data, Export Data, and I'm going to specify a file name. So I called it 1900 Contour, and it's going to be a shapefile, of course. Importantly, I'm only exporting the selected feature, not all the features. And I'll hit OK. I'll add it. So now I've got a new line that's going to just cover this 1900 contour. The next step is going to be to convert this line into a polygon. To do that, I'm going to go to Data Management, Features, and use Feature to Polygon. Input the contour, and then I'm going to give it a file name. I've called it 1900 Contour Polygon to let me know it's a polygon, not a line. And I'll just hit OK. Okay, and it completed that calculation. I'm going to zoom to the layer, and you can see that now I've got the entire area of interest above 1900 meters displayed as a polygon. And this is really going to act as a mask now that I can use to delineate which pixels are inside the polygon and which pixels are outside, so I can do my integration just on the pixels that are inside the area of interest. Okay, now we're at part 3, actually trying to compute the volume of this part of Shasta above the reference plane. There's a couple ways to do this. I think this intuitively simplest way is to first actually extract the part of the digital elevation model that we're interested in. So to do that, I'm going to use our old friend extract by mask. That's under Spatial Analyst, Extraction, Extract by Mask, and I'll enter my values now. Okay, so for my input, I've got the UTM projected DEM. For my mask, I've got the polygon that we just extracted. And for my output file, I'm calling it Shasta 1900, and I'm using the .tiff extension. I'll hit OK. Okay, so the extraction's finished, and it loaded the file automatically. Notice that now we have this new DEM that's actually clipped to the exact extent of the 1900 contour, and only has the elevation values for the upper part of the volcano. So the next step is going to be to convert these elevation values into delta Z values, or the actual height between the reference elevation and the surface. And to do that, we're going to go to our old friend raster calculator, which is under Spatial Analyst, Map Algebra, Raster Calculator. And we're going to write a very simple expression, which is Shasta 1900. So basically take the surface elevation of every pixel in the DEM we just created and subtract off 1900 from that. So subtract off the elevation of the reference plane. And it's going to do that calculation for every pixel. And I've given this a file name of Shasta Delta Z to let me know what I've got there, and I'll hit OK. Okay, so that new DEM has popped up. Now notice, instead of the elevation values that span from 1900 to 4300, the delta Z values span from roughly 0 to 2417. Okay, so now we've got our delta Z raster. We need to integrate the total volume of this raster. And it turns out that mathematically a very easy way to do that is just to recognize that the volume of this raster is given by the total area of the raster times the mean height, or the mean pixel value in this raster. And so how can we extract the total area of this as well as the mean height? To do that, we're going to use a tool called Zonal Statistics. That's also going to be under Spatial Analyst, down here under Zonal. And we're going to choose Zonal Statistics as Table, so we can output the data. Okay, so this first entry is actually basically the mask that you would like to use. In this case, I've entered in our polygon, 1900 meter contour polygon, and so we're going to get the statistics that are inside of this polygon. If this polygon had multiple features, we'd be getting the statistics for each feature individually. And then for the raster that we'd like to extract the values from, I've chosen, of course, our delta Z raster that we just made. And I've named the output table Shasta 1900 stats with no extension. I'll hit OK. Okay, that calculation finished, and noticed in doing so, it switched me from my regular table of contents view to this one called List by Source, where it actually shows the data source for each item in the table of contents. And it did that because the table is not visually displayed, it only exists as a link to a file. In any event, it is down here on the bottom. I'm going to right click and hit Open. Okay, and here's the table. Turns out that we got a couple different features in this table. I'm not sure why. I think there may have been a couple tiny features as part of the original polygon. So ideally we would have only had one feature row here, but it doesn't matter because we do have our main feature, which is this 9th row. What we can see here, it's showing us the pixel count. So we've got 2,271,000 pixels. That's going to give us an area of something like 204 million meters squared. And we've got a mean delta Z of 531. So I'm going to go ahead and take a minute and write down the mean of 531 and the area of 204,589,000 meters squared. Okay, when I multiply that mean height by that area, I get a volume of 108 billion meters squared, also known as about 108 kilometer cubed. So now I want to show you an alternate way to compute the volume using a direct integration in Raster Calculator. And what we're going to do is use Raster Calculator to make a new raster in which each pixel is equal to the volume rather than the delta Z. And so to do that, we're going to need to multiply the delta Z raster by the area of each pixel. So we need to first find out what is the area of each pixel. So I'll right click, go to Properties, and I can see that the pixel size here is 3.001 by 3.001 meters. So I'll write that down. And then I'll go over to our old friend Raster Calculator, which is under Map Algebra, under Spatial Analyst. And I'll write a very simple expression. And that is I'm going to create a new raster in which the values are equal to delta Z times 3.001 times 3.001. And that, of course, is the area of each pixel. So in this new raster, each pixel is going to be okay, I've specified a file name of Shasta 1900 volume, and I'll hit OK. Okay, so that calculation finished up, and we've now got this volume raster displayed. And the final step will be to once again use zonal statistics as table to actually add up all the volumes of all those pixels. So recall that's under Spatial Analyst, Zonal, Zonal Statistics as Table. Okay, so as my mask, I'm once again using the 1900 meter polygon. As my input raster, I'm now using the volume raster we just made instead of the delta Z raster. And my output file name is Shasta 1900 volume stats with no extensions. So I'll hit OK. Okay, so that table was exported. I'll right-click down here to open it. And you can see that one of the stats in this table is actually the sum. And in this case, that's the sum of all the pixels in the DEM. And it's a direct volume sum this time, and it gives us 108 billion meter cubed, which is the exact same estimate we got from our previous approach as well. So those two approaches gave us the same volume estimate. So in summary, our goal was to compute the volume of part of Mount Shasta. To do that, we defined a reference elevation, and then we defined an area over which we wanted to compute the volume. And then we actually computed the difference between each surface pixel and the reference elevation, that was delta Z, and multiplied that by the area of each pixel, summed them all up to get the volume of Mount Shasta. Thanks for listening. Join us for the next video where we'll start working with LiDAR data.